Welcome to Primax podcast number 81, and today we're looking at the fluid mechanics of hammerhead shark heads. So they're called cephalofoils. And the reason why this is interesting is because if you look at the hammerhead shark's head, it's there are different species, but in general they are quite flared on the side, and this actually creates a wing-like structure and actually helps them with swimming, or maybe it doesn't. I don't know. We'll find out in this podcast. So let's get started. So the paper we're looking at investigating this is called a hydrodynamics assessment of the hammerhead shark cephalofoil, so the head. And this is open access. You can find it in the link in the description. And as I mentioned, there are a bunch of different types of hammerheads. There's not just one hammerhead shark. There's like a whole family of them. In fact, there are two main families that have this type of head, generally speaking, and we'll cover them in this paper. So they say the function of the cephalofoil has historically been, so the hammerhead shark's head, cephalofoil. I'm just saying this a few times just to make sure that we will keep up to speed, because I didn't know that that's what it was called before looking into it. So the function of the cephalofoil has historically been a subject of much conjecture. In short, three general theories have been advanced to ascribe adaptive significance to this sphinid cephalofoil, so one type of hammerhead shark's head. So three different theories exist indicating why they have heads in this structure. The first one is that this structure has been hypothesized to provide sensory advantages by increasing olfactory, visual, and/or electrosensory abilities. And this is one theory that I was aware of. The second theory why hammerhead sharks have their heads in that shape is that observations of hammerhead shark behavior suggest that the cephalofoil may increase prey handling capabilities. The third theory is that the cephalofoil, the head, may serve a hydrodynamic function by increasing maneuverability and or providing hydrodynamic lift. And this paper looks into this third theory. So we talked about hydrodynamics, and something that is hydrodynamic is usually aerodynamic as well. There are some particular situations where that's not the case, but generally speaking, like 99% of the times, if it's hydrodynamic, then it's almost certainly going to be aerodynamic. And in this particular case, you can make that assumption as well, because there isn't anything really such as cavitation or anything like that happening with hammerhead shark heads. So the physics and the understanding that we use with aerodynamics maps very well into hydrodynamics, and it fits into the broader family of fluid mechanics. So because they lack a swimming bladder, elasmobranch, so there are a lot of technical terms in this, and you're going to enjoy hearing me struggle trying to speak these. I don't speak well at the best of times, so this is going to be good. So these types, this family, so sharks, skates, and rays, they must rely on other mechanisms for buoyancy regulation because they don't have a swim bladder, unlike other fish. One long-standing supposition, often stated as a fact, is that the cephalofoil acts as a wing, producing lift forces that aid the shark in maintaining vertical station in the water column. So in other words, this head they use to be able to maintain a certain position as they're swimming around. Indeed, in both profile and parasagittal section, each lobe of the cephalofoil resembles a cambered wing. A cambered wing is more convex on the dorsal surface, so on the top, relative to the ventral, so underneath, which causes air or water to accelerate as it passes across the dorsal surface. So we all know this, like the top surface of the wing is more curved than the bottom surface, which makes the wing cambered to begin with. So this increases the speed, resulting in lower pressure on the top surface, and then lift is produced, even when the wing is at 0 degrees angle of attack. So in spite of nearly a century of speculation, empirical data regarding hydrodynamic properties of the cephalofoil are strikingly scarce. Sounds pretty interesting to me. So two primary mechanisms have been proposed regarding hydrodynamic performance of the cephalofoil. The first of these suggests that it is to increase maneuverability by acting as an anterior steering wing. So in other words, a wing at the front of the body, anterior. In the second mechanism, the cephalofoil functions as a planing surface, contributing to the shark's achievement of neutral buoyancy by acting as a hydrofoil to generate lift. So one is saying that it's used to control direction. The other one is saying that it's used to control the force actually acting on the entire body. So those are two different things. For example, to draw a parallel to an aerodynamic situation for an aircraft. So the wings, for example, they are to produce the majority of the lift, whereas the tail is mainly just to change direction and control the stability of the aircraft. So that's an analogy there. To date, Only one study has sought to directly evaluate the hydrodynamic attributes of the cephalofoil and its capacity to generate lift. In that study, the lift-to-drag ratio for model representations of the cephalofoil of 8 hammerhead shark species were determined using a wind tunnel. So the lift-to-drag ratio is a measure of an airfoil or any body's efficiency, with a greater lift-to-drag ratio usually meaning a better efficiency. While results of that study suggested that the cephalofoil produces lift, data indicated that airfoil behavior was limited to high Reynolds numbers, so Reynolds numbers above 420,000, and the models were sculpted by hand. Vortex shedding was examined by using a flow tank, but again, the head models were handmade and experimentation was carried out over a limited range of angles of attack. Whereas in this report, they use CFD flow simulations to investigate the idea that the cephalofoil may produce an increase in maneuverability, that it may provide hydrodynamic lift similar to that of a cambered wing, and they calculate the drag and energetic cost of possessing a cephalofoil. So looking into the model, they have a CFD analysis of different shark species, and they got them from a bunch of sources. So 2 molds were used to cast plaster models of the shark heads of all 8 extant species of hammerhead sharks. And there are a bunch. I'll just quickly go through their Latin names: is E. blocki, S. corona, S. lewini, S. media, S. mocaran, S. tiburo, S. tudes, and S. zigana, as well as 3 carcinids species. And this is, okay, let me try to pronounce these ones now. C. locus, C. limbatus, and N. brevirostis. Okay, I hope I don't have to do that again. And they look at these different species, so in total 11 different sharks, at Reynolds numbers ranging from about 3,000 all the way, 30,000 all the way up to 200,000. And they looked at different CFD models. They range from 1 million nodes to 12 million. So they're fairly well resolved. I'm not going to go through the CFD because it's fairly standard. They just look at using RANs and URANs to solve. And it's fairly basic stuff for the CFD setup. So we don't need to go into any too finicky little details. If you want, you can look at the paper yourself, or we can just jump straight to the results. So I think we should jump straight to the results. So in the results, so let's zoom out so we can see both of these pictures. In figure 2, and again, if you are just listening to this, know that we have the video on YouTube, so you can look at the paper as we're going along with the video, or you can just listen to it and I'll describe what we're seeing. So in figure 2, we have 2 plots. The first plot, they're both color plots. The first plot has the top of each of these heads of these species of sharks, and the bottom plot has the bottom surface, and they're colored in the pressure. The pressure goes from -1 to 0.2, so it's normalized. And these shark heads range from being very pointy, so from like just kind of like almost actually like a bullet shape, which is head I, to a really, really hammerhead shark shape, head D, and it's very exacerbated. So it's very exaggerated, the shape. It's like it almost looks like an F1 front wing. And then they have a whole bunch of other hammerhead shark head shapes ranging between these 2 extremes. Now, they say qualitative comparison of pressure isosurfaces indicated similar pressure magnitudes at the angle of attack equals 0 over both the dorsal and ventral sides, so top and bottom. So this means that there's no lift being produced really at 0 degrees angle of attack for these heads in general, because the pressure on top cancels the pressure underneath. The pressure contours depicted the highest pressures across the dorsal surfaces, so the upper surfaces, near the central leading edge of the cephalofoil and just ahead of the mouth of the ventral surfaces. So in other words, if you look at these pictures, they have very high pressure actually at the front. Like if you think about where the nose is, that's where the high pressure is occurring. If you go to either side of the nose or downstream of the nose, the pressures drop dramatically. The large areas of low pressure were evident on both the dorsal and ventral surfaces of the cephalofoil, but at 0 degrees angle of attack, they kind of cancel each other out a little bit. So moving on to figure 3, they have the average pressure, area-weighted average pressures of the dorsal and ventral surfaces of the hammerhead shark heads at 0 degrees angle of attack for these different hammerhead species. So in other words, they reduced the pressure on one surface to one number and the pressure on the other surface to another number, and they weight through weighting it with the average of the area. And that way we can compare how much lift the bottom surface is producing compared to the top surface in a qualitative way, or a bit more quantitative, but it's not exactly all the way to do that. But we can see for certain hammerhead shark heads, the top surface is producing more lower pressure than the bottom surface, which means that there's a lift. But for other hammerhead shark heads, the bottom surface is producing a huge amount more, a lot less lift, I should say, than the top surface. So, for example, there's a head shark called S2des, where the bottom surface has a pressure of minus 0.7, whereas the top surface has a pressure of minus 0.08, perhaps. And let's look at what that head looks like. So this is the S2des E, and that is kind of like a hammerhead shark head, but if you just bring the sides in a lot. So instead of being very wide, it's just a little bit flared, not completely flared. And for some reason, this head produces a lot lower pressure underneath than on top. So we expected a very big downforce at 0 degrees angle of attack. They say that in 5 of the 8 hammerhead species, both dorsal and ventral pressures were less than 0. Excuse me. Mean dorsal pressures were higher than ventral pressures in 6 of the 8 species. And in most cases, dorsal pressures were much higher than ventral. So the upper surface than the bottom surface. The bottom surface pressures were higher than dorsal in only 2 cases. So in other words, even though these shark heads have similar geometries, it really depends on not just the plan form shape, but also the thickness and the airfoil cross section. So if you were to take cross sections through the head of the shark, these different cross sections will be different, and that changes the pressure developed. They also have figure 4, which is really cool. So it shows the planes at 0 degrees and 10 degree angle attacks for the pressure and velocity clipping through the heads. So they show the cross sections of the heads and how the pressures and the velocities change with the angle attack. So generally speaking, if you look at 0 degree angle attack, the pressures above and below the heads are fairly similar. They're somewhat symmetrical, not exactly, but fairly symmetrical. But when you push it to 10 degrees angle attack, all of a sudden there's a lot lower pressure on the top surface and the bottom surface, which is to be expected because these heads, the cross sections, look fairly wing shaped. They're not exactly wing shaped, but if I were to give an idea as to what airfoil they do represent, it would be like a supercritical airfoil in general, where the tail is very elongated and squished a lot. And in some cases, the trailing edge of these heads have almost like a flap, where like sometimes some of the heads they're pointed down, on other heads they're pointed up, and that's obviously going to change the lift being produced. Because, for example, if you take the hammerhead shark E, which was that hammerhead shark where there was a lot lower pressure underneath than on top, which means a lot of downforce, that hammerhead shark, the trailing edge is actually pushed up a lot. So it's like if you had a trailing edge flap and you put that up so you have a negative angle attack effectively. So that makes sense why this was producing a lot less lift and a lot more downforce than other sharks. Whereas for I, for example, this has a flap effectively which is pointing downwards. And let's go back to this figure that showed the pressures. If you look into I, which was the S corona, sorry, actually, no, that may not be it. The C limbatus, which was effectively just a bullet shape head. The C limbatus, they don't have plotted here, but I imagine that they would have a lot lower lift on top than on bottom. So that would be producing lift even as a 3 angle attack. Again, it depends on the cross section of the hammerhead shark. But at high angle attacks, so at 10 degrees, all of these cross sections seem to have an imbalance in the pressure, where the top surface has a lot lower pressure than the bottom surface, which means that all these heads are going to be producing lift, and we'll see that a bit later. I'm not going to give away too much, but there's just a little juicy tidbit for you. Oh no, now we're here. So in figure 5, we have the lift coefficient plotted versus the drag coefficient, and also the lift coefficient plotted compared to the angle attack. So when you have the drag on one axis and lift on the other axis, that's called a drag polar. And these are very common plots for aeronautic engineering. One of the major reasons why these are used is because they give you a lot of data in terms of understanding how efficient an aircraft is. And it's very easy to determine which aircraft or airfoil is the most efficient just based on the slope of the curve. So the greater the slope, the more efficient the aircraft or airfoil is. And what we see here is that generally speaking, there are three different categories of hammerheads. The first one is there are three different heads where they're producing very good lift to drag ratios. So they're very nice and steep with slopes. Then there's another group where they're okay, they're not as good, but they're still fairly good. Then there's one outlier, one hammerhead shark called E blocky or E blocki, which has a very bad drag polar where the drag is much greater for the lift that's being produced. So let's look at what head that corresponds to, and we'll see that as we go down, the E blocky is the quintessential hammerhead shark look. So it's a very exaggerated the head. So the wings are very fanned out to the sides, and it's the most exaggerated of any other head here. Also, that means that the aspect ratio of the head is very high. So the chord of the head is not nearly as great as the span. And even though for some reason it is producing a lot more lift, a lot more drag compared to the lift than the others. But if we go to the lift curve slope, so when we plot the angle of attack versus the lift coefficient, the E blocky or E blocki hammerhead shark, so the most exaggerated or most hammerhead-like shark, has the greatest slope for the lift coefficients. That means that the lift changes dramatically with the angle of attack. When we are at 0 degrees, it's actually negative, but by the time we get to about 21 degrees, it produces the most lift out of any of the other heads. Whereas the second best one, the S Morcaron, which is similar to the E blocki, but it's not as exaggerated, that produces high lift for almost all the angle attack range above 0, but it isn't as good as the E blocki when we get to very high angles of attack. So this head is very aggressive in its lift production. With that, we get the penalty of the increased drag production, which is often a trade-off that we have to make, where if we try to produce a lot of lift, even for our airfoils, we will get a lot of drag being produced at the same time as well, because we're just working the flow too much. And so that's common to see. So let's look at what they talked about. They said the drag increases with increasing angle attack at a much greater rate in the sphenids, so at a certain group of hammerhead sharks. At 0 degrees, lift coefficients for these sphenids range from a low of minus 1.085 for the E blocki to a high of 0.077 for the S tibero. And lift coefficients for the carchinids, which is another family, were essentially 0 at 0 degrees angle attack. Only the S Morcaron and the S Zigana cephalofoils showed positive lift of 0.146 and 0.1996 respectively at 0 degrees angle attack. Lift drag ratios were conspicuously lower across all angle attack for the winghead sharks, so the E blocki, than for other shark species. Now, one thing I want to point out is that the lift that they're producing is very impressive. So I mentioned that the E blocki, for example, that is the most aggressive in terms of producing lift and even downforce, but I didn't tell you how much lift it's producing. So at an angle attack of 28 degrees, it's producing a lift coefficient of about 4, which is, to give you an idea, that's better than pretty much any aircraft out there. If you look at a 747, for example, even with the wing flaps and the wing slats deployed at the greatest angle attacks that they can, we're only reaching like 2.8 or 3.2, depending on the aircraft. So lift coefficient of 4 is amazing. It's ridiculous. And the fact that they can do this while not having the flow separate completely is amazing as well. Comparing this to other hammerhead sharks, the sea limbatus, which let's go up to see what that head looks like. The sea limbatus head is I, so that's the bullet shape. This is the least effective in terms of producing lift, and we can see that with lift curve slope, where even at 28 degrees angle attack, lift is only like 0.9. So it's only 23% of what the E blocki can produce. So what that means is that the hammerhead shape is very beneficial for producing lift. If you were to compare these two, and then all the other airfoil, all the other hammerhead shark profiles fall in between these two ranges. So let's move on now. So they say, although their results suggest that the significant lift is not produced during horizontal swimming in the spherinids, the generation of lift at positive angles of attack during routine swimming can nevertheless be important. For example, the leopard shark, the Triachis semifasciatus, and the bamboo shark, Chiliosli. I'm not going to pronounce that. Let's move on. Held the body at plus 11 degrees and 9 degrees angle attacks, respectively, during horizontal steady swimming in a swimming tunnel to counteract the anterior ventral reaction force created by the heterocercal caudal. So, in other words, when they are swimming, they use their heads to stabilize themselves. That's what this means. To provide additional insight regarding potential hydrodynamic functions, they examine lift and drag across a wide range of angle attacks for all species. Modern-day human-made cambered foils are generally typified by C-shaped parabolic drag polars, drag values tending to increase concurrently with lift values as the angle attack becomes more extreme. Drag polars depicted in this study indicate that the drag typically increased at a faster rate than the lift. So this often happens when you're pushing an airfoil above its comfortable range of operation. So you're trying to like get a lot more out of the airfoil than what you typically get. This effect is imparted by boundary layer separation at the trailing edge of the foil increasing towards its center. This continues until flow separation ultimately occurs to such a great extent that the lifting efficiency, so the lift ratio of lift to drag, is undermined and the foil stalls. I just want to quickly touch upon this separation pattern. They said that the boundary layer separates at the trailing edge of the foil and progresses increasingly towards its center. This is true for thicker airfoils. So for hammerhead shark hammerhead shark profiles, I should say, these are fairly thick, and this is the stall pattern that we get. When you make the airfoil much thinner, we don't get this separation pattern, but hammerhead sharks don't have that thinner head shapes. If you have a very thin airfoil, you typically get much more catastrophic separation. So the entire airfoil will separate at some point, at the same point, or separation will occur at the leading edge, perhaps, depending on the airfoil profile. Of the hammerhead sharks, which approximate thick airfoils, this stall pattern is what happens. In previous work, no notable differences were observed across the drag polars of spheninid species, and little evidence of wing-like hydrodynamic properties of the cephalofoil among small sphenids was cited. In contrast, they observed substantial differentiation across sphenid species with regarding to both drag and lift polars, as well as substantial interfamilial differences. So in other words, the head does really make a big difference across the hammerhead shark heads are different across their families, and they do make a big difference to the lift and drag. In their examination of lift and drag coefficients, they observed a pattern whereby the curves were grouped broadly by the slope. The groups corresponded with sharks featuring discretely different head morphologies. So 1, the carcinids, 2, hammerheads possessing small cephalofoils, and 3, the hammerheads with intermediate cephalofoils, and then 4, the very large cephalofoils, so the E blocki. Across the species, the slope tended to decrease with decreasing aspect ratio of the head. So that's interesting. They said they likewise examined the relationship between the drag coefficient and the angle of attack. At the same angle of attack, the carcinid sharks were found to have the lowest lift and drag values, followed by the spheninid sharks with small and then intermediate sized cephalofoils. Then the E blocki, possessing the largest cephalofoil, was distinctly different, demonstrating significantly larger drag coefficients and showing the greatest change in the lift as angle of attack changed. So what this means is the E blocki, which has the most exaggerated head, even though it does like it's really pushing the boundaries. So it's acknowledging that okay, you're going to be getting a lot of drag, but the amount of lift that we're getting is worth it. So that's why we're doing it. And this is this evolution path of this shark. Whereas other sharks, the evolution path favored a more subtle head where they favored less drag. And we'll get into potentially why that is in a second. So in figure 7, this shows the pressure isosurface of one of the hammerhead sharks and some streamlines. And the reason why I show this is because they say the CFD post-processing included a basic check for wingtip vortex formations in hammerhead sharks at the ends of the cephalofoils, the wingtips. Streamlines generated from a particle trace depicting vorticity in some species at positive angles of attack for this species S. lewini. And the reason why I showed this is because I've mentioned in other podcasts and in other CFD videos that we've done particularly the one on hang gliders on our YouTube channel, I mentioned that a very good trick to determine whether an airfoil or something is producing lift is you just look at the wingtip. And if you get a wingtip vortex, like a bit of a spiral even of the streamlines, you can be certain that there is some lift being produced at this point. And we see that here. So we see that the streamlines around the wingtip of the hammerhead shark end, where the eye would be, there is some spiraling of the streamlines, and that's a dead giveaway that we are getting lift being produced. We are producing lift. So that's a very nice little trick. That's why I included it here. And these hammerhead sharks are producing these vortices as well, so they are producing lift as well with their heads. So, despite its common name, the E-block-eye cephalofoil generated the greatest amount of drag and produced at low angle attack the least amount of lift. So it was the worst at these angle attacks, but maybe note whether the E-block-eye head morphology displayed the greatest rate of change in lift coefficient as angle attack change, as mentioned, and at high angle attack they performed the best for the lift coefficient. The relatively rapid change in lift generated at positive angles of attack implies that the E-block-eye cephalofoil in particular may provide a hydrodynamic advantage via an increased maneuverability. So now they're discussing why this head is so different to the other heads. They say it may be significant that the E-block-eye diet was found to consist of about 93% of teleost fishes, apparently of the family Clupidae, whereas other hammerhead species fed predominantly on stingrays, crabs, and other bottom-dwelling organisms. So these teleost fishes, this is important because they are much more agile than stingrays, crabs, and other bottom-dwelling organisms. So the predominance of highly mobile fish in the diet of the E-block-eye may reflect the greater mobility that its cephalofoil provides. So in other words, even though the head does produce a lot more drag, because it allows it to maneuver much greater to catch these other fish, these more maneuverable fish, that allows them to feed quicker, to feed better, and that means that they can thrive. And this is actually similar to another hydrodynamic feature that I actually investigated many years ago. They're called tubercles, and they're found on humpback whales. And these tubercles are just bumps on the front of their flippers. And if you look up a picture on Google or DuckDuckGo, you'll see that these bumps exist on all humpback whales. And they start from about halfway, halfway on the F on their flippers, and they go out to the wing tip or the flipper tip. And what these do is they allow the humpback whale to swim at much greater angles of attack than if they didn't have them. And this they use during feeding. It's a similar sort of thing, because even though they do produce a lot more drag, they allow the humpback whale to produce a lot more lift and at high angles of attack, which means that they're more agile and they can catch their prey better, which means that they can feed better, and that if they get more food, they thrive. The exact same thing is happening here. So that's pretty cool. Even though they are different flow control devices, they have been developed for the same purpose. So previous research has concluded that the cephalofoil likely has a negative effect on stability. Its position at the far anterior end of the shark does increase its mechanical advantage substantially, and their results confirm that the magnitudes of the reaction forces produced increase rapidly as angles of attack deviates from 0 degrees angle of attack. So in other words, you have this lifting surface at the very front of the shark, and even a small force means that you're going to have a very strong rotational force, because the moment arm is so great to the center of gravity, the point where it rotates about. And these heads, like the E-block-eye, produces so much lift at such a far distance away from the center of gravity that this shark is very maneuverable now. The inference here is that the cephalofoil may serve as a forward rudder under active control of hypaxial and epaxial musculature. I don't know what that means. If you do know, let me know in the description. Thus providing for rapid dives and ascents. It should be noted that the cephalofoil may actually confer stability during turning, as it was observed that the sphinid sharks did not roll during sharp turns as did their carcinid counterparts. In other words, these heads, even though they are producing a lot of lift and they do produce a lot of drag, are a very stabilizing force in terms of the other directions that the shark may move in unintentionally. Actually, in the last podcast that I did, in podcast number 80, I talked about inertial coupling of aircraft, of drones in particular. And this is the same sort of thing where you change the direction in one way, it will change the other directions as well slightly because of inertial coupling. So this head allows the decoupling to happen, is what they're saying. So you can change in one direction and not have to worry about the changes that you get in other directions. So the larger hammerhead species are known to prey disproportionately on sharks and on skates and rays, and increased maneuverability could confer an advantage in avoiding such prey defenses of these skates and rays. They caution, however, that it remains uncertain from their results and other literature presently available whether or not the structure provides a prey capture advantage via increased maneuverability. So in other words, it may just be that they can avoid being hurt, but they may not be able to catch them quicker. Who knows? More research is needed. Different drags of the head's shapes. Let's talk about this topic now. Their calculations indicate that possessing a cephalofoil, which typically has a higher drag coefficient, requires almost 10 times increase in thrust for the S. lewini compared to a similarly sized C. limbatus shark. So let's quickly look at these two sharks, the S. lewini compared to the C. limbatus. So the C. limbatus is I, which is the bullet-shaped shark head. This S. lewini is a hammerhead shark, a very familiar type, not as exaggerated as the E. plocki, but still quite exaggerated. So it is noteworthy that the drag difference in this example is conservative since the S. lewini has a higher reference length and higher Reynolds number. It would be anticipated that the greater thrust and energy necessary for S. lewini to swim at the same speed as the C. limbatus would result in increased food consumption to offset increased metabolism and potentially a cascade of physiological changes that would accompany those increases. So in other words, because this shark produces so much more drag, it has to produce more thrust to just swim around. So it needs more food. However, various compensating mechanisms could offset the increased energy requirement of possessing a cephalofoil. For instance, hammerhead sharks may reduce cruising speed, enhance static lifting mechanisms, and or possess a more efficient metabolism. Also, if they catch their prey better because they're more agile, it means they can eat more. So it doesn't really matter if they burn more energy to a certain extent. That's another potential possibility. An interesting behavior has been observed in the S. mocharan, which is it's a similarly shaped head. It's a typical hammerhead shark type. These sharks have been reported to swim in situ on their sides for up to 90% of the time. This change in orientation during swimming may provide increased lift via the repositioning of the large dorsal fin, which is estimated to reduce the energetic cost of swimming by approximately 10%. So in other words, but instead of using their head to produce lift to maintain their current depth, so their buoyancy, they're using this to change their buoyancy. They swim on their side and they use their flipper, their shark fin, to produce lift instead. And this is potentially going to reduce the energetic costs by 10%. While it is not known if this behavior is widespread across these spheroids, so the typical hammerhead family, hammerheads in general possess relatively large dorsal fins relative to other shark species, and adopting this swimming behavior could relate to possession of a hydrodynamically costly cephalofoil. So in other words, using this instead of the cephalofoil may allow them to save some energy. So finally, the results of this study suggest that the hammerhead cephalofoil functions as a foil insofar as it operates as a symmetric foil, not a cambered one. So that means that at 0 degrees angle attack, it doesn't produce lift. It does not appear to possess sufficient camber to generate lift at this 0 degrees angle attack. Our analysis suggests that the possession of a cephalofoil may increase maneuverability, though. In light of evidence presented regarding active control of cephalofoil angle attack via the hypaxial and epaxial musculature, they suggest that this structure may function as a forward rudder and perhaps as a fluid dynamic brake, as the anterior end of the animal facilitating more rapid changes in position in the water column and increased maneuverability during the final moments of prey capture. So that means that the hammerhead shark's head doesn't just look good or doesn't just potentially house better electrosensors or whatever. It's also a hydrodynamic feature. And in particular, it produces a lot of lift and also some drag. So it makes it, generally speaking, more agile and also allows it to stay buoyant, even though it doesn't have a bladder, as other fish do. So that's the end of this podcast. Make sure to like, subscribe. And if you have any ideas that you want us to cover in our podcast, let us know. Otherwise, we've got a whole bunch of other things that are planned. And if you want to get better at CFD, check out the courses we do, link in the description. And if you do experiments or you do CFD and you need experimental validation, make sure to check out the Atmosphere Hawk, because that makes your experiments better by 2 to 4% and makes your CFD more accurate by 2 to 4% as well, or even more, because you're now comparing more accurate data. So link in the description as well. And I'll see you in this podcast. Peace out, amigos.